Hello, everyone. My name is Jonas. I work in the Blockstream research group, and this talk is about mainly two things: the recent addition of X-only public keys in BIP Schnorr, and how shortcuts in the music protocol can lead to vulnerabilities. And while we do that, we also look into concepts that can be useful in Lightning protocol research, namely security reductions and Wagner's attack. So due to the time constraints, I will go over some of the concepts very quickly, but the main goal of this talk is to give you an intuition when you read the BIPs or the documentation for yourself. This talk is about Bitcoin improvement proposals. In particular, we assume that a BIP taproot soft fork already activated on Bitcoin. BIP taproot defines SegWit version 1 output spends, and we don't care what these are, except that there's a new rule that you can spend outputs with Schnorr signatures as defined by BIP Schnorr. There's no guarantee that a BIP taproot soft fork activates in the current form or at all. This depends obviously on community consensus. Therefore, the question when this will be active doesn't make a lot of sense. So let's look at how compressed public keys work today in Bitcoin. A compressed public key is either the byte 2 followed by a 32-byte array, or the byte 3 followed by a 32-byte array. The first byte is called the tiebreaker, and the second 32-byte array is called is the x-coordinate of the underlying point on the elliptic curve. What is the purpose of the tiebreaker? A public key encodes a point on an elliptic curve. Given only an x-coordinate, there exist 2 points on the curve. The purpose of the tiebreaker is determine whether the encoded point is p or minus p. Recently, we changed BIP Schnorr from using compressed public key to what we call X-only public keys. The difference is that the tiebreaker is not part of the public key anymore. What we do instead is we implicitly assume that the tiebreaker is 2. Actually, in the BIP, a different tiebreaker is used, but that doesn't matter for the purpose of this talk. So why does this work? P and minus P are still different points after all. The public key point P generated by the secret key X is just X times the generator of the curve. And minus P is just minus X times G. So the answer is that we just need to negate public keys and secret keys at the right time. In particular, when the signing algorithm will check that we sign for the correct public key, and if we don't, the signing algorithm will negate the secret key before signing. There's no action required from wallet developers. It should be handled by the underlying crypto library. And also BIP32 derivation should work just as before, except that you throw away the first byte. So why do we do that? First of all, script pub keys are expensive in terms of weight units. X only saves about 0.7% weight units in average full blocks. Second, the cost for the sender to create a script pub key, taproot script pub key is the same as in pay-to-witness script hash, 136 weight units. In theory, adoption of taproot would be slower if it was more expensive to create taproot outputs. Pay-to-witness pub key hash script pub keys still have far less weight than taproot outputs because they only include the 20-byte hash of public keys, but that would be insecure for taproot. Just to complete the picture, if we take the witness weight into account, taproot and pay-to-witness pub key have about the same weight. And thirdly, there is no meaningful difference in the security level, as we will see now. So what we know is that in the random oracle model, if the discrete logarithm problem is hard, then Schnorr signatures are secure, which means that no signatures can be forged without knowledge of the secret key. Now what we want to prove is that if Schnorr signatures with compressed keys are secure, then X-only Schnorr signatures are secure. Or equivalently, if X-only Schnorr signatures are insecure, then Schnorr signatures are insecure. So we assume there is an algorithm that forges X-only Schnorr signatures as depicted on the right. Schnorr signatures are just a tuple. The first element is called the public nonce. You get it by multiplying the secret nonce, K, with the group's generator. And the second element, S, it's often called, combines the secret nonce and the secret key. The only part that's important here is that Schnorr signatures involve some kind of hash computation. What we're assuming now is that at some point the forger must compute this hash. There is no other way to produce a forgery. In order to define this correctly in formal proofs, the hash function is replaced with an idealized device called a random oracle. But for the purpose of illustration, we will continue to call this hash function. Now, what we have to do is we have to build an algorithm that responds to a challenger providing a compressed public key and returns a Schnorr signature forgery. We will somehow make use of the X-only Schnorr signature forger. It's just an algorithm. You can run it on a virtual machine if you will. Moreover, we can patch the forger's code that computes the hash function to return anything that we want. Now let's look at the first case, where the first byte of the public key is 2, the same as what we're implicitly assuming with X-only public keys. In that case, we just need to remove the first byte, pass it to the forger, let the forger do its thing, and pass the Schnorr signature directly back to the challenger. In the other case, the first byte is 3. Again, we pass the public key without the first byte to the forger, but now the X-only forger will decode the public key as -p. So the signature that will be created will be for the wrong public key. We fix this by programming the hash function to return the negative of the output of the hash function the challenger uses. Then we just wait for a reply from the forger and pass it back to the challenger. The negated hash results in a Schnorr signature for the non-negated original point P, so the challenger will happily accept the signature. To summarize, what we've shown is that if an X-only Schnorr signature forger exists, then a compressed public key Schnorr signature forger exists, or equivalently, we can assume X-only Schnorr signatures are secure. So now we're getting into the somewhat separate topic of how to implement the music protocol efficiently. What is music? It's a protocol that allows so-called key aggregation for Schnorr signatures. In the context of Lightning, for example, recall that the script interpreted when closing a funding transaction cooperatively involves 2 signature checks, 1 for each public key. With music, the channel participants create a single combined public key and just need to create a single Schnorr signature to spend it. Given a public key P and a message M, the signing for a music aggregated key requires 3 communication rounds. First, all participants exchange commitments to their nonces. Then, every node I reveals the public nonce Ri to everyone else. The combined public nonce is the sum of the individual nonces. Lastly, they exchange partial Schnorr signatures. If everything went correctly, the combined nonce and the sum of the partial signatures is a Schnorr signature. So having to go through the 3 rounds every time we want to sign a message is certainly inconvenient, especially if the signature is time critical or network messages are very slow. So how about this? We do the first 2 rounds whenever it is convenient for us, And as soon as we have a message to sign, we just do the last round, we exchange partial signatures. This is insecure. So what is the difference exactly? What goes into the hash is the combined public nonce, the public key, and the message M. The public nonce and the public key consist of every individual's contribution. But that means they are not biased by the attacker. However, we assume that the message M is under control of the attacker. So without pre-sharing nonces, this is not a problem, because the attacker has to choose the message M before they know what the combined nonce will be. And therefore, the output of the hash function is unbiased. Now, with pre-shared nonces, the attacker can choose the message after the combined public nonce is known and is therefore able to bias the hash function. Obviously, the attacker doesn't have full control over the output of the hash function, but even that little bit of control is sufficient. Now, let's move on to look at the concrete attack. Assume the attacker has an aggregated key with a victim and opens 3 parallel signing sessions with the victim. In each session, they go to the first 2 rounds and the attacker collects the combined nonces from each session. To be clear, in this case, the subscripts refer to the session index, not the signer index. Please bear with me. Then the attacker computes the nonce it's going to use for the forgery as the sum of the session combined nonces. Now, what the attacker has to do is find one message for each session, M0, M1, M2, such that the hash of his nonce, the public key, and his chosen message is equal to the sum of the individual round signature hashes. Is this hard? It looks hard. It looks like you would need some kind of hash collision, which would be hard. But it turns out it's not hard. The equation can be solved efficiently with Wagner's algorithm. With more than 3 sessions, with about 65 parallel sessions, only on the order of 2 to the 32, many operations are required to find a solution to this. Now let's continue with the attack. The attacker found such messages and the attacker provides them in their corresponding sessions. The victim proceeds with round 3, returns the partial signatures in each session, and now it turns out that the sum of the session nonces and the sum of the session partial signatures is a Schnorr signature forgery on a message the victim has never seen. Checking out the math is left as an exercise to the audience. There is one variant of pre-sharing that works, namely you only prepare the exchange of nonce commitments, and once there is a message to sign, you exchange the nonces. This still saves you 1 round trip on the critical path. So, in conclusion, BIP Taproot and BIP Schnorr were adjusted recently to work with 32-byte X-only public keys. This is relatively low level. Wallet developers don't need to care much about it. The security of X-only Schnorr signatures can be reduced to Schnorr signatures with compressed keys. Unfortunately, some creative shortcuts in music are insecure because the generalized birthday problem can be solved with Wagner's algorithm efficiently. Blockstream's music implementation in libsecp should be very difficult to misuse in such ways. BIP Schnorr and Taproot are slowly maturing from the draft status to the proposal status, so feel free to read the BIPs, implement them, or use the existing implementations. That's what I have for today. I don't know if we have time for questions. Thank you.
Hello. Maybe a bit of a concrete question. Let's say you have a channel opening with a coin join channel opening with, let's say, 100 participants. How big in bytes would the transaction be with music as opposed to how big would it be with like today?
Is this on? Okay. I think there is no actual difference, because I think what you're hinting to is signature aggregation, which is not what BIP Taproot or BIP Schnorr solve in any way. Because in a CoinJoin you have many inputs and many outputs, and these outputs all have some public keys. They can be aggregated or not with BIP Taproot. What we care about in CoinJoins is that the input signatures are aggregated, such that there will be only one signature. But that's not what BIP Taproot or BIP Schnorr solves in any way. That would be a different signature scheme. Hopefully 2025. Michael talked about it.
Any other questions? Can you guys pass?
Thanks. I didn't quite get the birthday reduction from SHA-2, 256-bit security to
This one?
with birthday means 128-bit.
Yes.
Finding a collision in 128-bit is quite not quite
Yes.
much more than 32-bit, right?
Yes, the trick here is that you're not trying to get a collision. You try to find a specific sum of many hashes, and that is an easier problem. So for three hashes, 3 parallel sessions, it's about 2 to the 100 operations. So what the attacker would do, he has to, so there's an optimal number of parallel sessions. In our case, it would be 65,000. And with 65,000, it's much simpler. This doesn't work on any group. So for example, you cannot do this in groups where the discrete logarithm is hard. But here, you're just adding up numbers.
Right.
Any more questions, guys?
Hi, I'm not sure about what I'm about to mention, but I believe this was an idea by James Chang, mentioned to Peter Wehler on IRC about the the X-only pub key. Is that correct? From James Chang?
I have no idea.
on
I mean,
IRC?
this has been a long-standing question: is when can we remove this additional byte? But we got the feedback on the mailing list that people wanted to see this, so we put in the extra effort. And I think it's worth it because you get this weight savings.
Yeah.
They are more than zero for free, basically. So
I just wanted to mention his name in case it was
Okay,
him, but I'm
okay.
not 100% sure.
Okay, follow him, James Chang.
Not me. James
James
Chang.
Chang.
James Chang. Yeah. He was a Chain Code resident last summer. Great guy.
Hi, I'm not sure how you can negate the private key if you don't ever get the private key together. Like if you have like this Taproot multisig, and if you combine different pub keys, then eventually maybe you end up on the different side
Yeah.
of the curve, right? So,
So
how
the
can
way
you
this works is just when music is set up between the participants. They add up their keys, they do the key aggregation, and then they just see whether their aggregated key is plus P or minus P, right? So they see this, and then they just either do nothing or all of them negate their secret keys.
All right, thank you guys, and thank you, Jonas.